Hey, I guess you knew it was going to happen. If you saw 2D vectors back in earlier presentations, then I guess you knew that we'd have to go to 3D space, come into this real world, mate. And if you haven't seen vectors before, well, welcome to Vectorland. And I want to reiterate here something that we picked up earlier. A very handy way of thinking about vectors are displacements of points on a plane or in space here now, in 3D space. So thinking of that. A vector is the displacement of a point on the plane or in space. And of course, let's have a look at how we're going to look at 3D space. And here we have it. Our set of axes has been enlarged, so our XY plane is laying down now, and the height there is Z. So can you get the idea of that? That's the convention we use, X, Y and Z in that direction. And we've tried to draw some actual surfaces in here to give you some idea of 3D-ness perspective there. And so come over here, and the idea now is that a point in space will have an X displacement from the origin, a Y displacement and a Z. And we still start with the point O, the origin, which is now 0, 0, 0. Everything's got three coordinates now, 3 dimensions. And of course, this little box method down here, you don't draw these when you're doing problems generally, because it's just actually too hard to represent 3D space on a 2D piece of paper. But it gives you an idea of here we come out on the x-axis, across the y and up the z, and you can see quite clearly there that the point P, x, y, z, those 3 displacements from the origin, is coming out of the page, if you like. And the box helps you see that perspective. All right, are you ready to go in 3D land? Let's have a look, because this is practical stuff now, because our world is 3D, of course. So just some warm-up questions here, trying to illustrate those points. Now just keep in mind, don't worry too much about doing this. This could actually be difficult and misleading when you're trying to do a problem. So you can see the idea here. You go 0 in the x, 0 in the y. So A, 0 in the x, 2 in the y here, and so A has gone nothing in the z, so it's sitting on the axis. Here B, 3, 0, 2, 3 in the x, nothing out here, and then 2 in the y, so it's sitting on the z axis. So you might start to think about equations for the axes. Okay, how do you describe the z axis, the x axis? We'll do a bit of that later on. And here's one with 3 coordinates, gone back in the x, 2 in the y, and then up to 3. All right, so come down and let's get rid of this fairly quickly, because it's fairly basic. Now, that's plotting the points. What about distances between points on the plane? Let's see what they are in terms of 2D distances. All right, so first of all, here we are. We have a point P, A, B, C plotted over here, and we've divided up some triangles. So here, point P has x coordinate of A, y coordinate of B. So we can find this here by Pythagoras. There it is, a squared plus b squared. OB squared equals a squared plus b squared. And then here we can go into this standing up triangle, OPB. Okay, and there we can see OP squared, which is this length here, OP squared is this one squared down here, plus this one squared. Okay, by Pythagoras. And we've already said OB squared from the triangle OAB is already a squared plus b squared from up here. Okay, so isn't that lovely? We've just repeated another Pythagoras and got a very similar expression to 2D distances, OP. And if you call these two general points A and B to do not the A and B over there, but any A and B on the plane, you could do the same thing. Change in X, change in Y, and change in Z. And you could do two Pythagoras applications as we did there, and you could have that. This delta is quite important later on, meaning change in, rather than Y2 take Y1, X2 take X1. So again, the formula for the distance between 2 points exactly parallels with the 2D formula. Okay, because you're just applying another Pythagoras application there. All right, so how's that? So we've got a formula now, and we're going to do the same sort of things as we did in 2D land, of course. Can we find distances? Can we find vectors, midpoints? So let's go and look at that. The midpoint, and we're not going to derive it here, is the same formula, of course, only with another dimension. Okay, so it's the average of the x's, the average of the y's between the 2 points, the average of the z. So what we've got here is point P, x1, y1, z1, and point Q, x2, y2, z2. I don't know whether you remember the derivation of this, but the midpoint and its ratios of distances travelled along the axes and using a similar triangle approach. So this is the midpoint here, midpoint M, and it's got the coordinates that we've got up there. And you could do that, extend that 2D proof to determine that, or to prove that. Okay, come down and let's get started on some little stuff. So here, if we have 2 points in space, find the distance. Okay, we're going to use that formula. Square root of x2 take x1 squared, plus y2 take y1 squared, z2 take z1 squared. Using the points here, just remember 1 take neg1 squared, 0 take 2 squared. You can do it in the opposite order. You could have neg 1 take 1 squared. It doesn't matter because you're going to square the results here anyway, but it's not a bad idea to keep it in the same order for each difference, because later on in certain areas it will matter, and it certainly will matter when we're talking about the vector A to B. Okay, coordinates of the midpoint, so there we have it, just the sum of the 2 x's, y's and z's divided by 2, the mean of the x movement, the y movement, the z movement. So that's fairly logical, and if you remember back to 2D proof, we do travel the average distance between the 2 points in both x, y and z. Okay, sorry about that. Okay, so come down and let's have a look now at just a couple of exercises to get you going. So I'd like you to try all of these. Pause presentation, have a go, and down below that I'm going to forward to in a minute are the solutions. I think you can breeze through these fairly quickly. Things like showing of vertices in an isosceles triangle, you've got to show that 2 sides are equal, but not the third. It's isosceles but not equilateral. Determine the nature of the triangle. The nature there is it could be scalene, no sides equal, 2 sides equal isosceles, or 3 sides equal equilateral. Okay, that sort of thing. All right, so pause it and have a go. I'm going to take you down here. Question 5, 6 and 7. Here's some interesting ones, and I was talking about that back on the first screen there, and that is what is the equation of various axes and positions. Okay, so you've got to go and find the region where z equals 3. Okay, so all the points where z equals 3, what would that look like in 3D land? Okay, so x equals 3 is a straight line, that's in 2Ds, but here z equals 3 and x and y, a member of R, could be anything. That's going to be extensive. That region, that locus, so these are often called loci, or the locus of points, plural loci in Latin. Where would you look for the points which have these various requirements? Okay, this is an interesting one down here. Okay, so have a go and see what you think. Pause it, and now I'm going to show you the solutions. Okay, so come down now and let's have a look at the solutions. Question 1. Let's go to question 2. Question 2, just check your numbers there. Got to get these numbers right. And question 3. Excuse me. Let's see all of 4 now. Oh, there's, hang on, we'll just go up a little bit more. I get 4 almost down to C. There we are, C. Okay, and D. and then we'll go to 5 and 6. Interesting little results there. And 7, 8. And question 9 is an important question to get your head around the 3D nature of the work that we're going to be doing. And let's look at E and F. Okay, some interesting shapes here. Need to study those. Talk about it with your teacher and classmates, because this is our new excitement. Well, the real world is 3D, and we can get some interesting shapes and stuff there. Okay, come down and let's go to part B. Sorry about that, we need to get rid of that. Three-dimensional vectors. Okay, so these screen clippings are from Hayes and Harris publications, so it'd be good to have that book handy. Okay, so here we are, three-dimensional. We're back in remembering what that means. A point is a point in space, so it has 3 coordinates, 3 plots away from the origin, if you like, 3 movements. So here, OP, the vector, okay, so here we are, we're considering vector OP, the displacement of the origin to the point P. That's the one way of looking at a vector as a displacement of a point in the plane. So this is called a position vector. Okay, and I don't think they make that here. Oh yes, here it is. Oh no, that's a different one. That when they say just a position vector, they mean from the origin to get to the point. So OP is position vector of point P, and you're going to get the x's, subtract them, the y's as x. What you're trying to do is to describe in 3D land how you got to the point, how you displace the point from the origin. Okay, delta x, delta y, delta z. And of course here, the first point in each case is going to be 0 if you're coming from the origin. But if you're going from A to B, then we say that's a position vector of B relative to A, or from A. That word can be a key word, from. Means you're starting there and you're displacing that point or travelling to the point from there. So that means this one would be x1, y1, z1 as the point, a curved bracket for a point, a square bracket for a vector, just remembering that. Okay, so that's what you're trying to do. Describe the displacement required to get one point to move to another, or to get to one point from another. Now get that idea of displacement here, that's important. Okay, if you're coming from the origin, it's called the position vector of the point. If you're coming from one point to another, it can still be called the position vector of B from A or relative to A. Have you got that jargon? Think about that. Okay, so it's an extension of 2D vectors, the same notion there. If you haven't seen that, you might go and have a look at that video first, because that leads you into this nicely. Alright, come down and let's have a look at what we can do. Here's a couple of examples. So we've got 2 points, and we want to find OA and AB. So OA is going from O to A, so it's the x of A minus the x of O, which is 0, the y of A minus the y of O, which is -1, and similarly for Z. So in other words, the position vector of a point A from the origin, or just a position vector, OA, is going to be the vector with the same values as the coordinates, isn't it? Because you're subtracting 0 in each case. What about AB? AB is the position vector of B from A, or relative to A. So you're starting at A and going to B. And so the movement is 1, take 3. And then 0, take -1. It's got to this time be in that order, because you're displacing A to the point B. So if you like, it's the x of the second point minus the first, y of the second point minus the first. And it must be in that order, because the displacement is specified as from A being displaced to B. And then watching these negatives there. So there's our vector. Okay, so let's have a look at lengths now. If you say OA has a length, it's the size of the vector, as we saw in earlier presentations, or you can just call it OA. And AB has a length, the modulus or size of AB, or simply AB. Okay, so we don't always put the modulus sign in, or absolute value sign. So here we are. P is that, Q is that. Find the size of PQ. Well, I think first of all, find PQ, moving from P to Q, displacing P to Q. So it's the x of Q minus the x of P, y of Q minus the y of P. Must be done in this order because it's got direction now. It's a displacement of P to Q, or the position vector of Q relative or from P. So we get it all as a vector, and then the size of it, as we said before, 3 lots of Pythagoras gives us the square root of the x coordinate squared, y coordinate squared, z coordinate squared. So just keep in mind there, if you have a vector, let's say vector A, and that is something like A1, A2, A3, then the size of A is the square root of the x coordinate squared plus the y coordinate squared plus the z coordinate squared, something like that. Okay, that's what came out of that earlier stuff with distances. Now you're ready to have a go. This is fairly simple stuff, so come down and have a go. Exercise 4b. I think you need to do most of these just to check off the basic calculations and getting the vector form. All right, pause the presentation, have a go at those, and I'll show you the solutions. Right, so come down and let's have a look at the solutions now. There we are, fairly simple problems. Just note we don't generally spend time in our work doing boxes to show it. You can't really get much from the box. You're just indicating here the 3D nature. You can't really spend too much time doing those things. All right, let's move on. Are you happy? 3D vectors, just extension of 2D, another coordinate, and some interesting things will come up though later on. So here we are, we have 2 points, and you want the position vector of A from, look, there's the key word, because it's starting at B, and it's displacing B to A, if you like. Okay, so there we have it. From B means you're starting at B and displacing, look at the arrow, displacing B to A. Okay, so what is it? B to A. So how do you get to A? Neg 1 take 2. So it's the x of the second point minus x of the first, y of the second point, and it must be done in the quoted order according to B to A. So this is A minus B in each case. Okay, because you're displacing B to A. And there it is there. So it's the second one minus the first. All right, and what's the negatives in here, the double negative? Okay, so as you go through that, you get that vector, and then the size of the AB, the size of AB, the size of the vector BA, and it's just the x coordinate squared, y coordinate squared, z coordinate squared. Okay, are you gearing up here nicely? This is a nice easy start to vectors, and there's some very interesting stuff coming up in 3D stuff. Okay, come down. Let's have a look at these 3 problems now. Very important, and this sort of thing here, you need to think about that, the distance of a point from the y-axis, so you need to think about where that point is plotted, and how would you get the shortest and the perpendicular distance here. The shortest distance is the perpendicular distance, so that's a clue, the perpendicular distance. Okay, so you might have to think about that. The YOZ plane. Okay, what is that? Okay, so have a go, pause the presentation. You might have to discuss some of these answers with your teacher and classmates. Alright, I'm going to show you the answers now. Come down and have a look at 4, 5 and 6. Okay, so there's 4 and 5. Okay, and finally 6. 6 is the interesting one. Distance of Q to the y-axis and so on. And just note here, you've got to take a point on the y-axis which is a perpendicular distance away from the known point. So here's a little diagram to show you what might be going on with part B there. Okay, alright, so how are you going? A little bit more to go, and then we're going to get into some good applications in 3D. So we need to get rid of this. Alright, okay, come down and let's do the last bit. So here we've done this before, geometric representation. O to A is bold in a book. We can do that, or use bold type, or you can do that, or you can do that as well. So any of those, we'll stick with the book notation this time round and do a little squiggle under the A. The magnitude or length can be represented by that, or we just say OA, or the size of A, or any of those notations. So this is just notation stuff now. So if A is that vector in bold, the size of A is the square root of the x coordinate squared plus y coordinate squared plus z coordinate squared, which was just the proof that we did right at the beginning. Alright, are you ready to do some representations? Let's do them. First of all, we'll revise something from 2D vectors. Two vectors are equal if they have the same magnitude and direction. So they could be anywhere on the plane. Remember, we said this before. When you specify a vector, it's often non-unique. If you just say the vector is here, it is here, A1, A2, A3, it doesn't necessarily specify where it starts on the plane. So here's vector A displacing that point. Here's vector A displacing a different point in the plane. And here, or in 3D space. And here's a vector A displacing a different point. And so when we have this specification, then we don't know where on the plane they are. They are going to be parallel and equal in length, because we are talking about equal displacements. Okay, so they've got to head off in the same direction and have the same magnitude. Alright, so if you say two vectors are equal, that implies the x displacement's equal, the y displacement's equal, and the z displacement's equal. Okay, so that's the idea. And this, of course, equal vectors implies that it's got to be parallel, because that's your direction of your displacement. Got to be the same length. That's the length of the displacement. So here we have a little picture over here. So therefore, this is an important geometric consequence. They're opposite sides of a parallelogram and certainly lie in the same plane. They can't be. Let's see if I can draw this now just nicely down here. Remember, that's x, that's y, and that's z. So you can't have one coming out there and one sort of coming under it. They don't intersect, but you know what I mean. You can't have one coming under it in a different plane. They've got to lie in the same plane. And when they do, of course, you're going to find that they form opposite sides of a parallelogram. So some interesting geometry here. And as we said before, geometry in this course, whether it be in complex numbers or whatever, is important, the geometric interpretation of what we're doing in each section of the work. Alright, see what you make of some problems. Come down here and let's have a look at what we can do. So here we've got unknown displacements. Here we've got A, B's and C's. And if these two vectors are equal, can we find out what those unknown values are? So we're saying that vector equals this one. So the x coordinate of one must equal the x of the other. X coordinate, that's wrong. X displacement, isn't it? The x displacement. And the y displacement has to be the same, and the z displacement has to be the same to make the vectors parallel. Okay, so then you can solve those equations. A is 2, B is 1, C is -1. So it's just trying to reinforce the equation of the components of the vectors, or the x components equated x displacements, equated y displacements and z displacements. Fairly straightforward stuff if you go back to your basic idea of vectors being displacements of points in the plane or in 3D space. Okay, come down and here's some for you. Okay, got some four questions here. Now, something like this here, you need maybe draw a little bit of a sketch, but not with boxes and so on. Yeah, see what you think, using the properties to determine whether there's something special about the quadrilateral. Has it got 4 equal sides? Has it got any parallel sides, and so on? So pause it and have a go. I'm going to show you the answers now. Okay, so here we have a few answers, question 1 and 2. Just the basic ideas there. And question 3 and 4. All right, very good. Let's go and do one more little problem here. And here's the problem type. And this is interesting. We've got A and B as points forming a parallelogram, and D, but one's missing. Okay, so could you find it? So the idea, of course, if you're trying to find the coordinates of C, let C be A, B, C, or something like that. A PQR, whatever. And so remember, the labelling of the diagram is always, here it is here, clockwise around the figure. You can't go A and then put B down here. It's got to have a rotation clockwise around the figure. You could go anti-clockwise in this case, but the convention is clockwise labelling around the figure and not go across the figure. So it's got to be A, then B, then C, then D. This is our convention, so we don't get confused with what we're talking about. It makes a difference otherwise. Okay, so there's our figure, and we've got to determine point C. So you can do some stuff because you know that it's a parallelogram, and so this AB is parallel to DC, going the same. Make sure you go A to B and D to C, and so here we've got DC equals AB in the same direction. Make sure it's in the same direction because we're using vectors, and that's important. Direction and also size. So get an expression for AB. Here it is, so put AB second. DC, of course, D to C will be A take 3, right, second point minus the first, B take 1, C take 4. Okay, so those 3 there, and they have to equal the displacement of A to B. Okay, the displacement of A to B in a parallelogram is going to be equal to the displacement of D to C. Obviously, let's scrub some of this out now and go back and say, well, you could have done it differently, couldn't you? You could have said AD, that vector equals BC, and done your equations that way. Okay, just noticing this means parallelism. Those two lines are parallel. Of course, if it's a parallelogram, these two would have been parallel as well. Just noticing the arrow on the end of the line means it's a vector displacement. So there's a different use of the arrows there. All right, so you can come up with the equations and solve those. And you could also do a little bit of a checking here. The midpoint of DB, so DB, that midpoint and the midpoint of AC should be common. The diagonals of a parallelogram bisect each other. So that means if you find the midpoint of one diagonal and the midpoint of the other, it should be, their point of intersection should be in common, and it does check here. Okay, so that's a nice little thing to do. Remember the midpoint formula, the average of the x coordinates, the y coordinates and z coordinates, average here of the x of A and C, y of A and C, and the Z of A and C. So starting to go into that geometry stuff again, so try to remember your coordinate, your 2D coordinate stuff as well. And let's have a look now at doing some problems on this. I've only got one for you here. I'll just hide that answer up there a little bit. Hang on, come down here. So we'll just go there, and can you find the missing vertex of this parallelogram? The missing vertex S. So it's just leading you into some more complicated figures where there might be some points missing, and you've got to use geometric properties and vectors to find them. Okay, so it's just a repeat of that example. So if you need to, go back and have a look at that example, and then check your answer. So come down here now, and we'll just check the answer. And there we have it. Just repeating the same sort of work that we had in that example. All right, so that's the end of our little introduction to 3D vectors. I guess it's an exciting move because you can see that it's more relevant to our real world, so we've got to get rid of this. It keeps coming up, I must fix that. So there'll be a number of presentations. I think there's 4 in all on vectors, and you're going to find the journey very interesting. So it's cheers for now. Catch you in the next one.